Alright, welcome back. This is Module 10, Chapter 7, Part 1. So this one's going to be slightly different, this video, because I want to show some drawings and so forth, and so you'll notice this video is slightly different. So this chapter really deals with the periodic table of the elements. And if you remember, we talked about a mole, and really a mole is a chemist's best friend. But the periodic table is actually one of the most significant tools that a chemist can use that helps organize and recall chemical facts. So the periodic table really arose from the periodic patterns in the electron configuration of the elements. So the trends within a row or a column form patterns that help us make predictions about chemical properties and reactivity. And so elements in the same column will contain the same number of outer shell electrons, or what we call valence electrons. Alright, so really this whole Chapter 7 is trends of the periodic table, okay, which I like to call a cheat sheet for chemists. And we're going to focus on three major trends, which is the size of atoms and ions, ionization energy, and electron affinity. Okay? And so a key principle in understanding the properties of atoms depends on electron configuration and how strongly the outer electrons are attracted to the nucleus. Okay? So I really want you to make sure that you remember this part. Alright, so when we talk about these trends of the periodic table, one of the things that we should note is as principal quantum number, which is called n, increases, the atomic orbitals become larger and less stable. Okay? And as the number of protons increase, any given orbital becomes smaller and more stable. Okay? And these two rules are really going to help us remember and apply to how effective nuclear charge is changes. So you should definitely remember that we have periods shown here, right, which go across, and most of these principal quantum numbers are kind of pretty much you can follow just the number on the period. And then we have our groups which go down, okay, and each group has the same number of valence electrons in each one, okay, where group 8A are noble gases and have a complete valence shell electrons. Alright, so a large majority of the properties of atoms depends on electron configuration and how strongly the outer electrons are attracted to the nucleus. So really to understand effective nuclear charge, we need to understand what's called Coulombs Law. Okay? And it describes the strength of an interaction between two electrical charges. And these are usually the nucleus and the electrons. Okay? Electrons are negatively charged and the nucleus has protons and neutrons. Well, the protons have this positive charge. Okay, and so if we know we have two electrical charges opposite, they're going to attract one another. Okay, and Coulombs law just says the strength of that interaction really depends on both the magnitude of the charges and the distance between the two. So as the nuclear charge increases, so as it becomes more positive, the force is going to increase. Okay, and if the electrons move farther from the nucleus, then the force is going to decrease. So if you think of an atom that has many electrons, then you can realize that the electrons are going to be attracted to that nucleus, right? Because that means it has a lot of protons, and so that negative charge is attracted to the positive charge. But at the same time, these electrons, the farther they are out, the more they are being repelled by the electrons surrounding it. Okay? So it's kind of a give and take relationship. And so the nuclear charge that an electron experiences is really dependent on both factors. So when we talk about the effective nuclear charge, we mean that it's the charge that's experienced by an electron on a many electron atom. Okay? And we can also define the effective nuclear charge with the equation, which is given here, which just says the effective nuclear charge, which is abbreviated capital Z with EFF, is equal to just the atomic number Z minus the screening constant. Okay? And the screening constant we can kind of think of more of just the core electrons, so the inner electrons. And so if we look at the figure shown here, we can see that if we look at sodium, the nucleus has 11 protons. So this little bit in here has 11 protons. We have 3 valence electrons, right? And it has a total of 11 electrons, which are attracted to this positively charged nucleus. So you can kind of feel those are just kind of being pulled in. Okay. Now the sodium atom contains 10 core electrons, right? And it just has this one electron in this valence electron shell. Okay? And so these 10 electrons inside are kind of screening this one valence electron from that positive charge. So we can take a look at this a little more detailed. Okay, so look at an example. If we look at sodium, okay, and we know that the electron configuration of sodium, based on the periodic table, we can look and we see sodium is down here. So if we write out the electron configuration, we know that we have 1s2, 2s2, 2p6, 3s1, right? And so we can kind of draw out what this would look like, right? And so we can first just draw our nucleus, okay? And that nucleus is going to have a number of positive charges. Then we can draw each of our electron shells. So first we can look at the 1, n equals 1, right? So we have 1s2, which means that we have 2 electrons in this first shell, okay? And so we'll put an electron here, and we'll put an electron here, okay? Then we go to the 2s, okay, and the 2p. So these are both the n equals 2, right? And so if we draw that electron shell, we have a total of 2 plus 6, so a total of 8 electrons here. So there's 1, 2, 3, 4, 5, 6, 7, 8 electrons in that shell. Okay. Then we can go to the n equals 3 shell. Okay. So this is n equals 1. N equals 3 shell, we only have 1 electron there. Okay. So if we draw that in, we just have this 1 electron hanging out. Okay. So at that point, we can say, okay, well, what does that mean for this 3s1 electron? Okay. So that is shown here, right? Well, that means A, it's being attracted to this positively charged nucleus. Okay. But at the same time, you have all these other negative charges from the n equals 2 and the n equals 1 shell that are kind of shielding this 3s1 electron. And so if we actually calculate out the effective nuclear charge, right, so ZeFF is equal to Z minus S, well, we can say, okay, well, we know the atomic number of sodium is 11, minus the number of shielding electrons, which are in those inner core electrons, which is a total of 10, right? And so we have a plus 1 effective nuclear charge. Now I want to turn and look at another example, which is magnesium. Okay. Now magnesium is right next to sodium, so we're moving across the period. Okay. And with magnesium, we know that our electron configuration is going to be very similar. We have 1s2, 2s2, 2p6, 3s2. Okay. And so once again, we can draw our atom, right? So here we have our positive charges, okay? And then we have our n equals 1, our first electron shell, okay? And in that we have 2 electrons, so we can draw the first electron, the second electron, okay? Then we can go to the n equals 2 shell, the second principal quantum number. In that one we have a total of 8 electrons. So once again we can draw in our 8 electrons. I know these drawings aren't perfect, but at least you can kind of see what's going on. And then we can go to our n equals 3, which we have 2 electrons here. Okay. For sodium, we only had 1 out there. So we're going to draw 1 here, and we'll draw 1 over here. Okay. So what we need to notice is that the shielding electrons are going to stay the same, right? Because we still have 10 core electrons. What changes is our atomic number, which is now 12 instead of 11. Right? By comparing the sodium and the magnesium, we have 11 versus 12, so we have more positive charge here in the center. Okay? So if we calculate that effective nuclear charge, take Z minus S, and what we find is that here we have 12 for our atomic number, minus the same core electrons, which is 10, And so now we have a +2 effective nuclear charge as we move across the period. Okay, so the shielding stays the same, but the atomic number increases across the period. So the effective nuclear charge then increases as well. Okay, so that's what happens if you go across a period. Well, as you go down a group, what's really happened is the electron cloud then becomes more diffused. So we could look at magnesium and calcium. Hey, let me clear this out for a second. Alright, so now if we turn and we look at magnesium and calcium, okay, what's going to happen is calcium is now going to have another electron shell, right, the n equals 4. Right, so if this is n equals 4, it's going to have 2 electrons in this shell. And for calcium, what's going to happen is that next inner set of core electrons is going to be filled now as well. Okay, and so now you're going to have more electrons in here, right, which is going to fill that electron shell. Well, when we really think about as we go down a group, we're saying the electron cloud is diffused. Okay, so what happens is electron repulsions are going to be more spread out. And this leads to an increase in the effective nuclear charge. Alright, so when we look at the trends of the effective nuclear charge, really what we can gather from this is that the effective nuclear charge increases from left to right across a period and will increase down the column of a group in the periodic table. Okay, and so we can just remember that the strength, okay, is across a period is going to be greater than down a column. So you can always remember across a period is greater than down a column. Okay, so that concludes part 1, and we'll follow up with part 2